Hello everyone, this is another ABAQUS tutorial. In this tutorial we are going to simulate a cyclic analysis of diagonally brassed steel frame. In a previous tutorial we have discussed how to conduct a chevron brassed frame. The difference between the diagonal brass and chevron brass is we're gonna explain this in a graph. This is a graph and this is the loading, which is, let me show you the example. This is a experimental work from these authors, and but I should say one more thing. I'm not going to simulate the same work, but my example is just a random example. In this work, the researcher conducted a cyclic analysis, and he put it one actuator here and then push it back and forth based on this loading. So at the first step is 0.25 that drift, and then 75 drift, and 2 and 4 6, and then it's equally this displacement 20 milli, 30, 60 milli, and the number of steps is quite large, about 1500 seconds. So we will discuss about all these things in our analysis as well. But after the result is come, so the result is like this. So this is the force, the vertical direction is force, and this is the displacement, horizontal displacement. But we have actually the tension area and the compression area. The compression area, you can see, is quite small, and the strength is about 40 kilonewton, because this sort of diagonal brass is very weak in the compressive loading. So it can, when you stretch it, you can stretch as long as you want, but when you compress it will be buckle. So this is the problem, and we want to see how the program or ABAQUS can provide such result for us. So we jump to the ABAQUS, but before that we're gonna show you here the example that we want to simulate is this figure with the beam from center to center is 4 meter and the height is 3 meter, and we considering to push back and forth about 2% of that drift. When we have the height is 3 meters and the 2% drift is about 60 milli. So I should say one more thing, why I took this one. In the 2% I can actually observe the inelastic response of this one, because the steel frame structure is maximum 1% drift, has a allowable 1% drift. So in that area just yield, and when we pushing 2, and that will be very larger in the inelastic part. So for this we created displacement loading. I have discussed a lot about this, how you can create this one, and I have provided a Excel sheet as well too, and then I can put this one to 2%. 2% is 60 millimeter, and I took this one 55 seconds, which is the total time need to the program completed this 60 millimeter displacement. So we jump to here and we create we can create actually 2-3 kind of element, using 2-3 kind of elements, such as solid elements, shell elements, and also wire. So for me, I suppose that the connection between brass and all the frame is rigid or gasket. You can see here there is no rotational or joint, anything else, just is completely fixed. So I use wire and just a frame, and the program automatically consider rigid. The unit I'm going to using millimeter, Newton, and ton. Now I want to extend this to let's suppose 8,000 millimeter, and when I draw 4 meter by 3, and it will be exactly this area. So I'm gonna create a line and giving point 0 0. When you draw point, is 2 point is okay. 2 0 0 and 1 point is talking. And the second is we go to up x is 0 and the height of the structure is 3,000 millimeter, and we are again going to 4,000 and 3,000 and that point, and again we come to 3,000 and 0. And now we finish the frame, and I'm gonna add one horizontal brass, diagonal brass. So this is the brass, and the modeling is completed here. So this is the rigid, the connectivity. We go to the property, and I will use Q steel 345, which has a still properties of 345 megapascal yield strength, and you can see here the density is here, which we using ton, and the elastic is 199 gigapascal, and the plasticity is we define this one. You can take the deterioration part as well, or you also can remove this and take the this ultimate strength and yield strength. So okay, and here we're gonna define some cross section or some profile. So first thing is column. So I should column. So the column is I section, and here is the size 300 300 12 10. So that means the wave and flange size is same, and the thickness of flange is 12 and the wave is 10, and the same for the beam is 300 200 12 10. So we go here, and this is the I, which is the generation radius, which is going to be off 150, and H 300 300, and this is also 312, this flange and this flange, and this is the wave T30. Okay, and we're gonna make one for beam the same, and we're using the height is 150, and here is 300, here is 200 200, and this is 12 12 and 10. Okay, and the last one is we called brass. The brass is T section, and we can check it here. The T section is 150 100 and 10 18. So there is also one actually one solution to prevent from this area, from this compressive, which we improve the compressive strength. We're using compact section. So then the compact section will not buckle until the primary beam and column yield. So in most of case we just use T. So now the size is 150 100 10 8. This is the B, which is 100, and this is 150, and this is which we're using 150 75, and the T is 10 and it's 8. Now we are done, and let me check one more. Yes, now we create a section. The first section is called column, and we're using beam, and then we take the beam, and the second is using column. Oh sorry, column was already exist, that we should change that one. Before that you can comes to here and edit it. So it's column, I took beam, so it should be column. Okay, and again we're gonna using called beam, and we take beam, and the last cross section will be brass. Now we are done here, and we want to assign this section to the members. So we select first the columns. You press shift, you can select multiple members. So column and beam, and the last one is brass. Now one more thing that we should add is the orientation. We add orientation, select all, and you can give this default and it will be in the right position. So we're gonna view this view and called part display in case the shape is different, so then we can change it. So you can see here is correct that what we expected. So now we are finished in the properties. We're going to bring it to the assembly, and we don't need anything in the assembly. We go to the step. So now we want to create some step in case if we have a gravity load, apply gravity load, considering some gravity load, then we have to create one step for the gravity load. So that means first applying the gravity load, and the second we will consider the cyclic load. So we don't have any gravity load. Even if you're considering the gravity of the self load of the structure, then we can say gravity analysis and a general static, and you can consider the nonlinear geometry as well, or otherwise no need. Now we're gonna create a second cyclic, we called analysis, and then in this time we can use static and also dynamic. But for this type of analysis is called quasi-static, which is between static and dynamic. So for this reason the program is quite comprehensive. There is application with the dynamic procedure, so quasi-static. I use this one, and you also can check the nonlinear geometry as well, because we're considering this. And here is the time period which we earlier discussed, to considering 55 seconds. So we're now putting this 55 seconds, and we're gonna go to the incremental. So we're gonna increase about 5,000, or maybe make it larger in case if the structure is yield, so there will be more increment, so you will not actually get error for this reason. So in a 10,000, so the initial should be 0.5, and the minimum is also can be a small number, minus like 10 or 15 like this. So the other thing is okay. We created two, and when you created two steps, so remember there should be two output, and the first output is actually we don't need it for the gravity. Even if you want, is okay, otherwise it's no need. So we're gonna cyclic analysis, and we considering a pre-default things, okay, and now we finished. And time history output, we're gonna go back to here. We wanna first create a node, a set, something called displacement, and I want to take this node, and I want to create one output in that point. When I'm gonna putting the displacement in this point, and exactly this point will give me a reaction force as well. So I'm gonna taking in the cyclic and asking that set, and increment should be 0.5. So what I want is displacement. I want the displacement in a direction 1 or ux, and reaction force also in the same direction. Okay, and this one is no need actually, because in case if we have more history output, so the program will take more time and also taking a lot of space. So now we're finished. In the step, we don't need anything in your interaction, and we go to the load. So the first thing is I'm gonna give the gravity load. So suppose we are giving gravity load in the gravity step. I can call it gravity load. Here it asks me select body for the gravity load. So which body you wanna take? So I'm taking the entire dive structure. So now you must give the G or the gravitation factor. So it's minus 9,800 because here is millimeter per square second. So we're using this unit. Now you can see here the gravity is added. And next I'm going to define the boundary condition. So I suppose the bottom is pen connection, and it can be from the initial. I'm going to select this point and this point, and here is called pen connection. And also in reality, one thing's in the program we are in a 3D dimension. In case if we do not restrain the lateral of the lateral, so the structure will deform in that direction as well. So in reality there is other column and also the floor, so we must restrain the lateralism, or laterally we should support it. And if you come to this program, if you come to this here, and you should see that top, this one is actually and this area here is laterally supported this frame. So this is much more practical, and I should create one displacement in this here. I just give U3 and I select this point and this point and just give U3 and creating a lateral support. So now the program will be in a 2D dimension. So the next thing is I should give a displacement in this step. I can call it displacement. So I select the seed which we already defined, and I give this one with unit of 1. Now here ask me to create a amplitude. So we already provided this one. I'm going to copy this and pasting here. Now you can see here. So selecting that amplitude. Now it's added. Now we finished the loading. We go to the meshing and we create some mesh. It's depending, it'll be part, and using this one is 500. You can use 200, a little fine mesh, and mesh it. So the mesh is completed, and we meshed. Come here and it's meshed. Now we go to the job and create the job and submit it. Frame. You also can increase the CPU, so but mine is okay, keep as a default. So it has me the S3 output is not requested. It was my intentionally I didn't put them. I'm gonna call yes, continue without that. Now it's start running, and I'm going to monitor it, and if in case if there is any error, I'm going to fix. Otherwise we can lead the program to finish. Yeah, the program is, it asks me there is too many attempts made for this increment. So this is the reason, too many attempts made for this reason, because there is so many reason. So I should say that I want to fix this one. So when you want to solve this problem, you mostly come here in here, and first in the gravity load turn on this one. The second, come here and come here, and also you comes to the in the loading. This loading, for in my opinion, is not correct, so I should change this. I'm gonna delete this one, and I wanna, it was line load, it was actually wrong. It should gravity load, should be this one, and I'm gonna give gravity load. That was quite large and program cannot convert. It's going to minus 8010 or like this. Now it's okay. You can see here the gravity sign is like this. Now the program will work. Now we can monitor it. Yes. Now the first step is start. It's finished because the gravity load is start work, and the second step is also begin. Yeah, you can see here. It take a while, and after the analysis completed, so then we will check the result and we will discuss. Now the analysis completed, and it took almost 1 hour and 6,000 increment. So in a earlier we said let's put 10,000, so that will not get any error. Now we go to the result, and we can here result. So here is the result in the last step. So this is the result. Let me render these elements, and you can see clearly. And obviously the brassing is totally yield. Even you can see the active yield, so you can check the entire brasses yield. And we also can go to the displacement and do some lists in a 3D form, and we want to see this one, the animation. And if we make a little list 5 times, the deformation should be 5 times increased, and you can see the buckling will be seen in this brassing. Yes, and this is the buckling, and you can see the brass is totally buckled, and that cause the compressive part should be smaller than the tension part. So we're gonna again, and so it will be repeated during the cyclic loading. So I'm gonna stop because it's take 6,000 steps, quite large, and we go to the create and ODB output, and we already giving in the time history that to that node displacement and also reaction force. Create, yeah, reaction force and displacement, plot it, and you can see the curve. And then we wanna use the operation and combine this one, and the displacement be in a x direction and reaction force be in the y direction. So I'm going to save it as a hysteresis curve, and we called OK, and OK, and I'm going to plot it. And now you can see exactly the same curve is created by the simulation. So here the number of the step or number of step is quite large, and hour is 2%. So here is 2, 4, 6 minus our side is here. So now you can see here few cycles, and like this you can draw the resistance curve. And so this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time.